like to present the project of eBPF-based observability for serverless WebAssembly workloads, which belongs to work package 2. Observability refers to reading data from a system to understand its current state. The observability is usually realized by application-level instrumentation. One way is manual instrumentation, where the developer needs to add tracing calls to the application source code. The problem is that there might be missing code instrumentation if the developer forgets. The other approach is auto-instrumentation, which is usually instrumentation in library, so it cannot guarantee full code coverage. Also, both approaches can lead to large volumes of unuseful data. The system-level instrumentation usually just produces host-level metrics. However, eBPF UProbe allows applications-level tracing and can be utilized to support instrumentation-free observability for WebAssembly workloads. So we propose our observability framework, which leverages eBPF UProbe technology to support observability. The observability target is serverless WebAssembly workloads running in Kubernetes using SpinCube. The data collector is also deployed as WebAssembly module. The utilization of eBPF can minimize the footprint of observability because the traffic filtering and preprocessing is near the source of data. The positioning in overall architecture is shown like this. The observability system is designed for Kubernetes environment. Integration with Kubernetes is illustrated in this figure, where Kubernetes control plane orchestrates the workloads running in worker nodes. The workloads could be Linux containers, or in our case, WebAssembly-based applications running on top of Bing runtime, and they are called Bing apps. Our key contribution is the eBPF-based agent that collects data from the Bing apps. The eBPF agent is deployed locally on each worker node as a daemon set to allow filtering and preprocessing of data. Here's the system architecture with more implementation details. First, the UProbe is attached to the functions of Bing runtime, which are some socket-level functions including receive, write B. Then eBPF program is triggered when the function is called. Then the trace data is collected by eBPF program and written to ring buffer. Next, the agent reads the trace data from the ring buffer and it filters error code such as 404, preprocesses and sends data to Kafka service. We also have considered the scenario of tracing a service chain, and in this scenario, extra HTTP headers are added to requests. To demonstrate the prototype, we deployed 3 Bing apps in the Kubernetes, which constitute a service chain. Now I would like to show the demo of the prototype. The Bing apps and eBPF agent have already been deployed. Now we send the HTTP request to the Bing app, and then the traces are captured by eBPF and sent to UI dashboard, as we can see here. And the trace look like this. As we can see, it concludes information such as the error code and error details, which can be used for further analysis. We also evaluated the system performance. Under worst-case scenario, our eBPF-based solution introduced a maximum CPU overhead of 8% and average HTTP response time overhead of 17.9%. More explorations can be done in the following 3 directions in the future. First, currently filtering of HTTP error is done in the user space proxy. Filtering in the kernel is problematic but might be more efficient. Second, our framework is not 100% instrumentation free. Also, our framework brings some user space to kernel space context switching overhead with UProbe. So experiment with alternatives to eBPF can be done, but this is beyond grant agreement. The alternatives can be observing WebAssembly completely in user space without eBPF. For example, using FreeDA library, or implementing dynamic instrumentation directly in the runtime. But whether these alternatives are more efficient are not yet proved. Anyway, they will bring some extra latencies. Thank you.